Time is not the steady river we feel it to be. Near a black hole, it stretches into a slow-motion syrup, and space itself warps around massive objects like soft fabric. This is the strange realm of cosmic relativity, a field that challenges our most basic perceptions of reality. Albert Einstein once marveled that the most incomprehensible thing about the universe is that we can comprehend it at all. This journey through 35 groundbreaking insights will give you a complete new framework for understanding the cosmos, from the bending of spacetime to the enigma of dark energy. We will see how these ideas not only redefine physics, but also hint at the ultimate nature of existence. What if the flow of time is just an illusion, and could the entire universe be a projection from a distant boundary? How does your perception of reality shift when you consider that the past, present, and future might all exist at once? That heavy ball on the trampoline is more than just an analogy. It is a fundamental rewrite of reality. Einstein's great insight was that what we perceive as the force of gravity is not a pull at all, but a consequence of geometry. The sun, a massive object, creates a deep well in the fabric of spacetime. The Earth does not orbit because it is magically attracted. It simply follows the straightest possible path through the curved geometry of that cosmic well, a path we call an orbit. This idea, formalized in his general theory of relativity in 1915, completely overturned centuries of Newtonian thought. It was no longer a mysterious force acting at a distance, but matter and energy dictating the very shape of the stage upon which the cosmic drama unfolds. The physicist Kip Thorne captured this beautifully when he said, "Spacetime tells matter how to move, matter tells spacetime how to curve." This is a continuous, dynamic conversation between the contents of the universe and the stage they perform on. The mathematics describing this curvature involves complex objects called metric tensors, which are essentially the rulebook for measuring distances in this warped landscape. These rules are governed by the Einstein field equations, a set of formulas that precisely link the curvature of spacetime on one side to the density and flow of matter and energy on the other. One of the earliest and most dramatic confirmations of this came during a solar eclipse in 1919. Scientists observed that light from distant stars passing close to the sun was not traveling in a straight line. The sun's gravity was bending the starlight because the light itself was following the curved geometry of spacetime. This phenomenon, called gravitational lensing, proved that even massless light is subject to this cosmic curvature. This is not just abstract theory, it operates in your pocket every day. The global positioning system in your phone has to account for these warping effects. The satellites in orbit experience time flowing slightly faster than clocks on Earth's surface, a direct result of spacetime being less curved further from the planet. Without constant corrections for this time dilation, your GPS would be inaccurate by several miles within just a few hours. So if spacetime is this malleable fabric, what does that say about the universe's true structure? It suggests a cosmos that is dynamic, flexible, and deeply interconnected, a living entity where geometry is destiny. This realization that space and time are woven together into a single, pliable entity forces us to confront an even stranger truth about the other half of that fabric. A second, identical clock ticks away aboard a spacecraft hurtling at a tremendous fraction of light speed. When that ship returns to Earth, a profound strangeness awaits. The clock that traveled along with the astronaut holding it has recorded less time than the one that stayed behind. This is not a malfunction, it is the undeniable reality of time dilation, a core principle from Einstein's special theory of relativity established in 1905. Time itself is not the rigid, universal metronome we assume it to be. Its flow is personal, dependent entirely on your state of motion and the gravitational field you are in. This leads to the famous twin paradox, where one twin who travels on a high-speed journey through space returns to find their stay-at-home sibling has aged significantly more. The equations governing this are the Lorentz transformations, a mathematical framework that shows how measurements of time and space compress and stretch from different perspectives. We see this in two distinct flavors. Kinematic time dilation occurs purely from relative motion. The faster you move through space, the slower your clock ticks relative to a stationary observer. Gravitational time dilation, which we touched on earlier, occurs because time flows slower in stronger gravitational fields, like near a planet compared to far out in space. These are not just theoretical ideas. In the 1970s, scientists placed incredibly precise atomic clocks on commercial airplanes. After the flights, these clocks were compared to synchronized ones on the ground, and they showed a tiny but measurable lag, exactly as relativity predicted. On a much grander scale, particle accelerators provide daily confirmation. Subatomic particles called muons, which are created when cosmic rays strike our atmosphere, have such short lifespans that they should decay before reaching the ground. Yet, because they are traveling at nearly the speed of light, their internal clocks slow down so dramatically from our perspective that we detect them in abundance. So how does this ripple into your daily life? Every time you use a GPS for navigation, the system is actively correcting for these relativistic effects. The satellites are both moving fast relative to you and are in a weaker gravitational field, causing their onboard clocks to run at a different rate than those on Earth. Without these constant adjustments, the entire system would fail in minutes. This fluidity of time forces a deep philosophical question. If the passage of time is not absolute, but a personal experience that changes depending on where you are and how you are moving, can we truly say the past is fixed or the future is unwritten? Perhaps all moments simply are, existing in a vast four-dimensional block universe. The physicist Brian Greene captured this personal nature of time perfectly, stating, "Time is personal. It is your own journey through the cosmos." And on that journey, nothing sets the ultimate speed limit for your travel quite like the cosmic constant that makes all of this possible. Nothing in the cosmos can outrun a beam of light. This speed, a constant 299,792 kilometers per second in the void of space, is the universe's ultimate traffic law. It is not merely a speed, it is a fundamental feature of reality's structure, denoted by the letter c. Einstein's great revelation was that this speed is invariant, meaning every observer, no matter how fast they are moving, will measure the exact same value for the speed of light. This single, stubborn fact is what shatters our classical notions of space and time. It forces time to slow down and lengths to contract for objects approaching this limit, all to preserve this cosmic speed limit. The noted cosmologist Carl Sagan once reflected that the speed of light is not just a fact about light, it is a fact about causality. It is the speed limit for cause and effect itself, ensuring that a signal cannot arrive before it is sent, preserving the logical order of the universe. Why is light so privileged? The answer lies in its masslessness. Particles with no rest mass, like photons, are compelled to travel at this maximum speed from the moment of their creation. They do not accelerate, they simply are, born racing at the universe's top pace. Any particle with mass, however, can never quite reach this velocity. It would require an infinite amount of energy to push even a single electron to the speed of light, a physical impossibility. This is why the famous equation E equals mc² is so profound. It reveals that mass is simply concentrated energy, and that c² is the conversion factor, the price tag for turning one into the other. We see the implications of this constant every time we look at the night sky. The light from a distant quasar has been traveling for billions of years to reach our telescopes. We are not seeing it as it is now, but as it was when the universe was young. That light is a fossil, a messenger from the deep past. This creates a profound challenge for interstellar communication. If a civilization existed around a star 100 light-years away, a simple hello would take a century to arrive, and our reply another century to return. Conversation is practically impossible across such distances. If we could somehow exceed the speed of light, we would not just be breaking a rule, we would be shattering causality. You could theoretically travel back in time, potentially creating paradoxes where you prevent your own journey. The fabric of reality, the very sequence of events that gives our lives meaning, relies on this unbreakable barrier. This unshakable connection between light speed, energy, and causality leads us directly to one of the most powerful and famous ideas in all of human thought. That single letter C, the cosmic speed limit, is the key that unlocks the universe's most powerful equation. E equals mc² is far more than a collection of symbols. It is a revelation that mass and energy are not just related, they are two different faces of the same fundamental entity. Einstein published this insight in 1905 as a direct consequence of his special theory of relativity, and it forever changed our understanding of reality. The equation states that energy, E, is equal to mass, m, multiplied by the speed of light squared. The speed of light is an enormous number, and squaring it produces a truly astronomical conversion factor. This means that even a tiny amount of mass contains a staggering amount of locked-away energy. The physicist Lisa Randall captured this perfectly, noting that E equals mc² is a statement about the convertibility of mass and energy, revealing the hidden potential in matter. To understand this, we must look at the concept of rest mass. This is the intrinsic mass an object has when it is not moving. According to the equation, this rest mass itself represents a vast reservoir of energy. When we talk about mass in this context, it is important to distinguish it from the outdated idea of relativistic mass, which increases with velocity. Modern physics focuses on the invariant rest mass, as this is the true measure of an object's energy content. We harness this convertibility in powerful ways. In a nuclear reactor, the process of fission splits heavy atomic nuclei. The total mass of the resulting fragments is ever so slightly less than the mass of the original nucleus. That missing mass has not vanished, it has been transformed directly into a tremendous amount of energy, which we then use to generate electricity. The same principle works in reverse. In giant particle accelerators like the Large Hadron Collider, we pump massive amounts of energy into collisions. That pure energy can then condense back into new particles of matter, often creating forms that have not existed since the Big Bang. The most profound demonstration of E equals mc² shines in the sky every day. Our sun is a colossal fusion reactor, constantly crushing hydrogen nuclei together to form helium. In this process, a fraction of the mass of the hydrogen is converted into pure energy. Every second, the sun transforms over 4 million tons of its own mass into the light and heat that sustains life on Earth. This single process has been powering our solar system for billions of years, all governed by that one elegant equation. So we must ask, what other cosmic engines are driven by this mass-energy conversion? Could the violent jets from black holes or the explosive fury of supernovas be fueled by the same fundamental principle? This realization that matter is frozen energy forces us to see the entire cosmos as a dynamic, interactive system. And if matter and energy are so deeply intertwined, how does the most dominant force in the cosmos, gravity, fit into this picture? Einstein's equations held a final, hidden prediction. When two massive objects spiral together, their violent dance does not happen in silence. It sends literal ripples through the fabric of spacetime itself, distortions that travel outwards at the speed of light. For a century, these gravitational waves were just a mathematical ghost, an unconfirmed consequence of his theory that changed on September 14, 2015. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal. It was a tiny chirp, a vibration smaller than the width of a proton, but it told an epic story. Two black holes, each about 30 times the mass of our Sun, had collided over 1 billion light-years away. Their final inward spiral, merger, and ring-down created a storm in spacetime, and we had just heard its echo. Rainer Weiss, who shared the Nobel Prize for this discovery, called these waves the universe's way of talking to us, and it is a completely new language. Unlike light or radio waves, gravitational waves are not blocked by cosmic dust. They pass through everything, bringing us unedited information from the most violent events in the cosmos. This marked the birth of multi-messenger astronomy, where we can now both see and hear the same cosmic catastrophe. The waves are generated by accelerating masses, much like a moving electric charge creates electromagnetic waves. The strength of the wave, its amplitude, depends on the masses involved and how fast they are accelerating. The frequency tells us about the scale of the event, from the rapid chirp of stellar mass black holes to the low rumble of supermassive black holes merging. The first event, known as GW 150914, was just the beginning. Soon after, LIGO and its European counterpart Virgo detected the collision of two neutron stars. This time, telescopes around the world and in space saw the accompanying flash of light and gamma rays, confirming that these collisions are the cosmic forges where heavy elements like gold and platinum are created. These observations are like turning on a new sense. We are no longer just watching the silent movie of the universe, we are now listening to its soundtrack. What else might these ripples reveal? Could the faintest gravitational wave background hold secrets about the universe's first moments after the Big Bang, a time before light could even travel freely? Might they even give us clues about the nature of dark matter, if it interacts in ways we have not yet imagined? These subtle vibrations in reality are our direct line to the cosmos's most dramatic moments, and they lead us inevitably to the objects that create the most profound ripples of all. At the heart of our own galaxy, a silent monster lurks. We now know this as Sagittarius, a star, a supermassive black hole with a mass 4 million times that of our Sun. Its existence was painstakingly confirmed by tracking the frantic orbits of stars around an apparent point of nothingness, a place where the grip of gravity becomes absolute. This is the realm where general relativity is pushed to its breaking point. The boundary around a black hole, the event horizon, marks the point of no return. Cross this invisible threshold, and the curvature of spacetime becomes so extreme that all possible paths lead inward. Not even a beam of light traveling at the universe's ultimate speed possesses the energy to climb back out. This creates the black hole's shadow, a dark silhouette dramatically captured by the Event Horizon Telescope in its image of the black hole in galaxy M87. But what happens to all the matter and energy that falls in? According to our current understanding, it is crushed into an infinitely dense point at the center, a singularity. Here, the laws of physics as we know them cease to function. Space and time themselves lose all meaning. This stark reality highlights a fundamental conflict between Einstein's theory of gravity and the quantum laws governing the very small. Yet, Stephen Hawking made a startling discovery, showing that black holes are not completely black. He theorized that due to quantum fluctuations near the event horizon, black holes can slowly leak radiation and evaporate over astronomical timescales. This Hawking radiation suggests that black holes have a temperature and a lifespan, blending relativity with quantum mechanics in a tantalizing way. We observe different classes of these gravitational giants. Stellar mass black holes formed from the collapsed cores of massive stars can be just a few dozen miles across. Supermassive black holes, like the one in our galactic center, are the engines at the heart of most large galaxies. As matter spirals inward, it forms a superheated accretion disk, a whirlpool of plasma glowing with intense radiation. Sometimes, this process powers enormous jets of particles that shoot out from the poles at nearly light speed, stretching for thousands of light years across interstellar space. These cosmic behemoths are more than just destructive vacuums. They are essential architects of galactic structure. Their gravitational influence is thought to govern the formation of stars and the very shape of their host galaxies. Could their extreme warping of spacetime also create bridges to other regions of the cosmos or other universes entirely? The theoretical possibility of wormholes, though likely unstable, hints that black holes might be gateways rather than merely final destinations. This exploration of ultimate gravity inevitably draws our gaze outward to a force that operates on the grandest scale of all, a force that is not pulling the universe together but tearing it apart. The universe is not merely expanding, it is accelerating away from itself in a runaway cosmic sprint. For decades, astronomers assumed the mutual gravity of all matter would eventually slow this expansion, perhaps even reverse it. Then, in the late 1990s, two independent teams studying distant stellar explosions made a shocking discovery. The most remote supernovas were significantly dimmer than expected, meaning they were farther away than anyone had predicted. The expansion of the cosmos was not slowing down, it was speeding up. This revelation, which earned its discoverers the Nobel Prize, pointed to a mysterious, invisible agent acting against gravity, a force we now call dark energy. Cosmologist Adam Rees, one of those Nobel laureates, called it the biggest mystery in all of science, a puzzle that challenges the very core of our physical theories. How do we know this? The key evidence came from Type 1, a supernova. These are the thermonuclear explosions of white dwarf stars, and they have a remarkable property. Because they all explode at nearly the same critical mass, they all reach nearly the same intrinsic brightness. This makes them perfect standard candles, cosmic lighthouses of known wattage. By measuring how dim they appear from Earth, astronomers can calculate their precise distance. When they compared these distances to the redshifts of the supernova's host galaxies, a measure of how fast those galaxies are receding, the data told an unmistakable story of an accelerating universe. This acceleration implies that roughly 68% of the cosmos is composed of this dark energy. It behaves like a sort of anti-gravity, a repulsive force woven into the fabric of empty space itself. Einstein himself had stumbled upon this idea with his cosmological constant, a term he originally inserted into his equations to create a static universe, later calling it his greatest blunder. Now it seems he may have been right for the wrong reason. The cosmological constant suggests that empty space is not truly empty. It possesses a fundamental energy density that pushes the universe apart. Another theory proposes that dark energy is a dynamic field nicknamed quintessence which could change over time. The ultimate fate of the cosmos now seems tied to this enigmatic force. If dark energy continues to dominate, the acceleration will intensify. Galaxies outside our local group will eventually be pushed away so fast that their light can no longer reach us. The universe would face a cold, isolated end known as the Big Freeze, where the cosmic sky goes dark. This profound discovery forces us to ask, is dark energy a permanent feature of spacetime, or is it something that evolves? To find answers, we must look back to the very beginning, to the afterglow of creation itself. That faint, cold glow filling the cosmos is the oldest light in existence. It is the cosmic microwave background radiation, a direct echo from a time when the universe was a dense, hot soup of particles, just 380,000 years after the Big Bang. Before this moment, the universe was so hot and dense that it was opaque, a searing plasma where light was constantly scattered by free electrons. But as expansion cooled the cosmos, electrons and protons combined to form the first neutral atoms. In that instant, dubbed recombination, the universe suddenly became transparent, and that first burst of light has been traveling through the expanding cosmos ever since, cooling to a mere 2.7 Kelvin above absolute zero. Its discovery in 1965 was almost an accident. Arno Penzias and Robert Wilson at Bell Labs were troubleshooting a persistent, faint hiss in a giant radio antenna, a noise they could not eliminate no matter what they tried, even cleaning out pigeon droppings from the horn. They had inadvertently stumbled upon the remnant glow of creation itself, a finding that earned them the Nobel Prize and provided the smoking gun evidence for the Big Bang theory. Cosmologist George Smoot perfectly described this radiation as the baby picture of the universe, a fossilized snapshot of its infancy. But this picture is not perfectly smooth. Embedded within it are tiny temperature variations, anisotropies that appear as slightly warmer and cooler patches on the sky. These minute fluctuations, on the order of 1 part in 100,000, are the seeds of all cosmic structure. They represent regions of slightly higher density, where gravity's pull was just a bit stronger, eventually drawing in enough matter to form the vast cosmic web of galaxies and galaxy clusters we see today. Missions like the Planck satellite have mapped these tiny ripples with exquisite precision, creating a detailed all-sky map of this ancient light. These maps do more than just show us the seeds of galaxies, they also reveal the geometry of the universe. The patterns in the cosmic microwave background are a direct test of cosmic relativity, and they strongly indicate that the universe is geometrically flat. This means that on the largest scales, parallel beams of light will never converge or diverge, a finding that perfectly aligns with the predictions of the inflationary model. Furthermore, the polarization of this light, a specific direction of its vibrations, tells us about the very first instance after the Big Bang. Some patterns in this polarization are thought to be imprints from primordial gravitational waves, the ripples in spacetime generated during a period of hyper-fast expansion. So what does this ancient whisper tell us about the universe's explosive birth? It confirms a dramatic growth spurt in its first fleeting moments, a process that stretched the fabric of spacetime itself, smoothing it out and planting the quantum seeds for everything to come. This foundational evidence points us toward the mechanism that must have set it all in motion. The ancient whisper of the cosmic microwave background points to a universe born in a frenzy. To explain its profound uniformity and geometric flatness, physicists propose a breathtaking cosmic growth spurt known as inflation. This theory suggests that in the first sliver of a second after the Big Bang, the universe underwent an exponential expansion, doubling in size perhaps 100 times or more in an unimaginably brief interval. Alan Guth, who first proposed the idea, described it as the ultimate free lunch, where a tiny, primordial patch of space was stretched to a scale larger than our entire observable universe today. This explosive stretching smoothed out the cosmos, ironing out any initial wrinkles and leaving behind the nearly perfect homogeneity we see in the cosmic microwave background. It also drove the geometry of the universe toward flatness, just as inflating a balloon makes any small patch on its surface appear flatter and flatter. This single idea elegantly solves the horizon problem, the puzzle of why regions of the universe far apart today could have ever been in contact to achieve the same temperature. Before inflation, those distant spots were once close neighbors, able to share heat and reach equilibrium before being violently pushed apart by the inflationary surge. The engine for this incredible expansion is thought to be a hypothetical field called the inflaton. Picture this field as a kind of cosmic landscape where the early universe found itself perched high on a hill, filled with a tremendous potential energy that exerted a powerful repulsive gravity, forcing space to expand at a ferocious rate. The dynamics of this roll down the hill are governed by what physicists call slow roll parameters, which essentially measure how gradually the inflaton field lost its energy. A slow, gentle roll was crucial, as it allowed the inflationary period to last long enough to create the vast, smooth cosmos we inhabit. As the field eventually reached the bottom of its hill, this stored energy was released, reheating the universe and filling it with the hot plasma of particles that would eventually form atoms, stars, and us. One of the most thrilling predictions of inflation is the generation of primordial gravitational waves. The violent stretching of spacetime during this epoch would have created ripples that still echo through the cosmos today. Scientists search for the imprint of these waves in a specific pattern, called B-mode polarization, within the cosmic microwave background. Detecting this faint swirl in the ancient light would be a direct glimpse into the universe's first instant, a smoking gun for inflation. The implications of this theory stretch beyond our own cosmic horizon. Andre Linde, a key architect of inflationary models, noted that once inflation starts, it may be eternal, giving rise to a vast multiverse where countless bubble universes are continuously being born, each with potentially different physical laws. Our entire observable universe, with all its galaxies and stars, may be just one bubble in an infinite, frothing cosmic sea. This rapid expansion did more than just smooth and flatten. It also amplified tiny quantum fluctuations present at the birth of the universe, stretching them to cosmic proportions. These magnified ripples in density became the gravitational seeds for all future structure, the blueprints for the first stars, and the great cosmic web of galaxies. So we must ask, if inflation planted these seeds, what was the invisible scaffold that allowed them to grow into the majestic structures we observe today? The stars at the very edge of a spiral galaxy are racing around its center at impossible speeds. According to the laws of gravity, these outer stars should be moving much more slowly, like planets in our own solar system that crawl along in their distant orbits. Yet observations show they whip around just as fast as the stars near the bright core. This cosmic conundrum points to a profound truth. The galaxies we see are embedded within vast, invisible halos of something else, a substance we call dark matter. The astronomer Vera Rubin provided the most compelling evidence for this, meticulously measuring the rotation of galaxies and stating that the stars at the edges move too fast, implying unseen mass. This missing mass does not emit, absorb, or reflect any form of light, making it completely invisible to our telescopes. Its presence is felt solely through its immense gravitational footprint. The story of dark matter began even earlier, in the 1930s, when Fritz Zwicky was studying the Coma Cluster, a giant collection of galaxies. He noticed that the individual galaxies were moving so quickly that the cluster's own gravity should not have been able to hold them together. He concluded that some unseen form of matter, which he called Dunkel Materie, must be providing the extra gravitational glue. So what could this mysterious substance be? The leading candidates are hypothetical particles that do not interact with the electromagnetic force. One prominent idea is WIMP, or weakly interacting massive particles. These would be heavy particles that rarely bump into ordinary matter, streaming through you and everything around you by the billions every second without a trace. Another candidate is the action, a particle that would be incredibly light but also incredibly abundant. Scientists are trying to catch these ghostly particles using incredibly sensitive detectors buried deep underground, shielded from cosmic rays. They wait for the exceedingly rare moment when a dark matter particle might nudge an atomic nucleus. Another line of evidence comes from gravitational lensing, where the gravity of dark matter warps the light from galaxies behind it, creating distorted arcs and multiple images, a natural telescope magnifying the distant cosmos. Perhaps the most dramatic proof of dark matter's existence comes from cosmic collisions like the Bullet Cluster. This is a system of two galaxy clusters that have smashed right through each other. The ordinary matter, in the form of hot gas, was slowed down by friction and now sits in the center, but the dark matter, which does not interact with itself or the gas, has sailed right through. By mapping the gravitational lensing, astronomers could see that most of the mass is now separated from the visible gas, a clear sign that the mass is in a form that is fundamentally different from anything we know. This invisible scaffold does not just hold individual galaxies together, it governs the largest structures in the universe. The great cosmic web of galaxy clusters is woven together by the gravitational pull of dark matter. Its presence in the early universe acted as a gravitational anchor, pulling in ordinary matter to form the first stars and galaxies. This raises a deep question: what if dark matter interacts with ordinary matter in ways we have not yet imagined? Could there be a hidden dark sector with its own forces and particles, a parallel universe of matter existing all around us? The search for its true nature is one of the greatest quests in physics, forcing us to confront the limits of our current theories and pointing toward a deeper union between the cosmos and the quantum world. Deep within a black hole where gravity becomes infinite, our understanding of reality breaks down completely. This is the frontier where Einstein's smooth, geometric universe of general relativity collides with the fuzzy, probabilistic world of quantum mechanics. To describe the fabric of spacetime at this ultimate scale, we need a theory of quantum gravity. The physicist Carlo Rovelli observed that quantum gravity is not just another theory, it is a necessary step to understand the fundamental nature of reality. Without it, we cannot truly comprehend the core of a black hole or the first instant of the Big Bang. Two of the most prominent approaches to this grand challenge are string theory and loop quantum gravity. String theory proposes that the fundamental constituents of the universe are not point particles, but incredibly tiny, vibrating loops of energy. Different vibrations of these strings correspond to different particles, like electrons or photons, and one particular vibration is thought to produce the graviton, the hypothetical quantum carrier of gravity. This theory requires extraspatial dimensions, curled up into sizes near the Planck scale, which is the unimaginably small distance of 10 to the negative 35 meters, where quantum gravity effects dominate. In contrast, loop quantum gravity takes a different path. It does not propose any new particles or extra dimensions. Instead, it suggests that space itself is not continuous, but is woven from a fabric of finite, discrete loops. Picture the smooth spacetime of general relativity as a piece of fabric. Under an extremely powerful magnifying glass, this fabric would resolve into individual threads. Spacetime, in this view, is granular, made of tiny, interconnected quanta of space. This granularity could resolve the troubling singularities at the center of black holes, replacing the point of infinite density with an ultra-dense, but finite knot of spacetime. This quest leads to one of the most perplexing thought experiments in physics, the black hole information paradox. Stephen Hawking showed that black holes slowly evaporate through radiation, seemingly destroying the information about what fell into them. But quantum mechanics insists that information can never be truly lost. This creates a stark contradiction between the two foundational theories. The resolution may lie in the holographic principle, a radical idea that suggests all the information describing a volume of space can be encoded on its boundary, like a three-dimensional movie being projected from a two-dimensional screen. If this is true, then our perception of a three-dimensional universe might be an emergent illusion, with space-time and gravity arising from a more fundamental, information-based reality. Could it be that the universe is not built from tiny bits of stuff, but from tiny bits of information? This profound question pushes us to consider an even deeper layer of existence, where the very concepts of location and distance may be derived from a cosmic quantum entanglement that connects every part of the cosmos. This holographic view of reality turns our intuition about the universe inside out. The information needed to describe everything within a volume of space, every star, every person, every atom, could be entirely encoded on its two-dimensional boundary, like the data on a DVD projecting a rich, three-dimensional movie. This radical idea, known as the holographic principle, was born from the thermodynamics of black holes and developed by physicists Gerard T. Hooft and Leonard Susskind. Susskind captured its profound implication, stating that the holographic principle implies that the world is like a giant quantum computer, suggesting that information is the most fundamental currency of existence. The seed for this idea was the discovery that a black hole's entropy, which is a measure of its hidden information, is proportional not to its volume, but to the surface area of its event horizon. This was bizarre. In everyday life, the amount of information something can hold scales with its volume, like filling a hard drive. But for a black hole, the ultimate container, the maximum information it can contain is limited by the area surrounding it. It is as if all the data about what fell in is painted onto the surface of the horizon, and our three-dimensional reality is a projection from that cosmic screen. This principle finds a concrete mathematical home in the AD/CFT correspondence, a duality in string theory. It proposes that a gravitational theory in a hypothetical anti-de Sitter space, which is a universe with a negative curvature, is completely equivalent to a conformal field theory, a quantum theory without gravity, operating on its lower dimensional boundary. They are two different descriptions of the same underlying reality. One description has gravity and curved spacetime, the other is a flat quantum system. This means that spacetime itself and the force of gravity may not be fundamental, but may emerge from the complex quantum interactions of particles on a distant surface. A key player in this informational picture is entanglement entropy. Quantum entanglement, that spooky connection between particles, is now understood to be intimately tied to the fabric of spacetime. The entanglement between different regions of a quantum system on the boundary is what weaves together the geometry of the spacetime in the bulk. If you were to reduce the entanglement between two regions, the space between them would literally begin to pinch off like a cosmic thread being cut. This suggests that the connectivity of our universe is fundamentally quantum and informational. So what does this mean for the cosmos? Some cosmological models apply the holographic principle to the entire universe, proposing that we may all be living on a vast, two-dimensional shell at the edge of the observable universe. The galaxies, planets, and your own sense of a three-dimensional world would be an incredibly detailed and convincing illusion generated from this underlying code. This forces a deep philosophical shift. Is the universe fundamentally made of information, of bits, rather than of substance? Are the laws of physics simply the operating code of a cosmic quantum computer? If our reality is a holographic projection, then the very stage we stand on is an emergent property, a consequence of a deeper, information-based reality. This realization that our universe might be one of many possible projections naturally invites a staggering question: what lies beyond our cosmic horizon? Our universe could be a single bubble in an endless, frothing sea. This is the staggering proposition of the multiverse, a theory suggesting that our cosmos, with its specific laws and constants, is just one of a potentially infinite number of universes in a vast cosmic ensemble. The concept emerges naturally from two ideas we have already explored: the eternal nature of cosmic inflation and the many possible solutions within string theory. Cosmologist Martin Rees elegantly captured this scale, noting that our universe may be just one bubble in a cosmic froth. Max Tegmark has helped popularize a useful classification, organizing these possibilities into 4 distinct levels. The Level 1 multiverse is perhaps the simplest to grasp. It is simply our own infinite space. If the cosmos is truly infinite, then every possible configuration of matter must repeat somewhere far beyond our horizon, meaning there are countless copies of you, me, and everything we know existing in distant patches of space. Level 2 arises from eternal inflation, where different pockets of space stop inflating at different times, each forming a separate bubble universe with its own unique physical laws and constants, like separate soap bubbles in a sink. Level 3 comes from the many worlds interpretation of quantum mechanics, where every possible outcome of a quantum event actually occurs, but in a newly branching parallel reality. And Level 4 is the most radical, suggesting that all mathematically consistent structures actually exist as physical realities, making our universe just one of an infinite set of all possible universes. But if we cannot visit these other worlds, how could we ever know they are real? Scientists look for potential footprints. One tantalizing possibility is that our universe might have once collided with another bubble, leaving a bruise, an anomalous pattern in the cosmic microwave background. While no definitive evidence has been found, the search continues. This expansive view directly confronts the mystery of fine-tuning. Why do the fundamental constants of nature, like the strength of gravity or the mass of an electron, seem so perfectly calibrated to allow for stars, planets, and life? The multiverse offers a profound answer. If every possible set of laws exists somewhere, then it is no surprise we find ourselves in one of the rare, hospitable universes. This is the Anthropic Principle in action. We observe a universe compatible with our existence because we are here to observe it. Does this mean the quest for a single, elegant theory of everything is futile, or does it open a new chapter in our understanding of reality? The possibility of a multiverse forces us to confront the very nature of existence and our place within it, leading us to wonder about the precise cosmic recipe that made our own universe possible. The fundamental numbers woven into the fabric of our universe appear suspiciously perfect. If the force of gravity were even slightly stronger, the cosmos would have collapsed back on itself in a fiery crunch long before stars could form. If it were marginally weaker, matter would have flown apart too quickly to ever coalesce into galaxies. This exquisite balance extends beyond gravity to other cosmic constants, like the strength of the electromagnetic force, quantified by the fine structure constant, approximately 1 over 137. This number governs how atoms hold together. A tiny change in its value would prevent the formation of the stable carbon atoms that are the bedrock of life as we know it. Even the vacuum energy, the energy of empty space that drives cosmic acceleration, is fine-tuned to an astonishing precision of 1 part in 10 to the power of 120. Physicist Steven Weinberg captured this eerie precision, noting that the universe seems to be balanced on a knife edge. This is the puzzle of fine-tuning, a mystery that challenges our very understanding of why the universe is habitable. Consider the process of nuclear synthesis inside stars. For stars to forge the elements of life like carbon and oxygen, the nuclear forces must be calibrated just so. There is a resonant state in the carbon nucleus that allows 3 helium nuclei to fuse into carbon efficiently. If this resonance were off by even a fraction of a percent, the universe would be filled with mostly hydrogen and helium, with no heavy elements to form planets or people. This is not a matter of simple chance. It feels like a cosmic recipe was carefully followed. So what explains this apparent fine-tuning? One compelling answer lies in the multiverse. If an infinite number of universes exist, each with its own random set of physical constants, then it is no surprise we find ourselves in one of the rare, hospitable ones. This is the Anthropic Principle in action, a simple selection effect. We are here to observe this universe precisely because its laws allow for observers. Another, more controversial interpretation is that a cosmic designer set the dials. Yet for many scientists, the multiverse provides a naturalistic, if mind-boggling, explanation that fits within the framework of modern cosmology. This profound fine-tuning does more than just explain our existence. It forces us to confront our place in the cosmos. Are we the product of unimaginable cosmic luck, or merely one outcome in an infinite ensemble of realities? This delicate balance that allows for complexity and life is intimately connected to another great cosmic mystery, the relentless forward march of the arrow of time. A shattered egg never pulls itself back together. This simple, irreversible fact points to a deep cosmic truth, the arrow of time. Why does time have a one-way direction, flowing from the past we remember into the future we cannot see? The answer lies in a concept called entropy, which is the measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. The universe, from a broken egg to a dying star, moves relentlessly from order to disorder, but this raises a profound puzzle. Why did the universe start with such incredibly low entropy in the first place? Cosmologist Sean Carroll frames this as the past hypothesis, the idea that the universe began in a very special, highly ordered state at the Big Bang. That initial low entropy wound up the cosmic clock, giving it a direction to unwind. Think of it like a deck of cards perfectly arranged in order. Shuffle it once, and it becomes slightly more disordered. Shuffle it 1,000 times, and it will never spontaneously return to that original, perfect sequence. The entire history of our cosmos, from the formation of galaxies to the processes of life, is powered by this great slide from order into chaos. This cosmic expansion itself generates entropy, creating more and more room for disorder to increase. As space stretches, it fuels the journey toward the eventual heat death of the universe, a distant state of maximum entropy where all energy is evenly spread out and no further work can be done. The connection to black holes is especially deep. A black hole's event horizon possesses an immense amount of entropy, far greater than the star that collapsed to form it. When matter and information fall into a black hole, the total entropy of the universe still increases, even as those things vanish from our view. This ties the arrow of time directly to the most extreme gravitational environments. But what if the universe is vast enough for statistical flukes to occur? This leads to the strange thought experiment of a Boltzmann brain. In a truly random and eternal universe, it is statistically possible, though incredibly unlikely, for a fully formed, conscious brain to spontaneously assemble from random particle collisions, complete with a set of false memories. The fact that we are not such Boltzmann brains, but instead exist in a universe with a clear past, is more evidence that our cosmos began in a very specific low-entropy state. This directionality is woven into our very consciousness. Our memories are records of the past because that is when entropy was lower. Causality itself, the rule that cause must precede effect, is enforced by the arrow of time. Could time flow backward in some other part of the cosmos? It seems unlikely, as the initial low-entropy condition of the Big Bang set the arrow for our entire observable universe. This relentless march from order to disorder, from a definite past to an uncertain future, forces us to look back toward the ultimate beginning, to the moment where the laws of physics as we know them were born, the point of infinite density where time itself may have begun. At the very heart of a black hole, the equations of general relativity scream in protest, predicting a point of infinite density and zero volume. This is a singularity, a place where the smooth fabric of spacetime is torn apart and our current laws of physics simply cease to apply. These regions are not just mathematical oddities. They are the ultimate frontiers where gravity becomes so overwhelmingly powerful that the quantum world must take control. The physicist Roger Penrose, in his groundbreaking singularity theorems, demonstrated that under very general conditions, such singularities are an unavoidable fate for massive collapsing stars. Once a star's core collapses beyond a critical point, no known force can prevent its complete and utter descent into a singularity. We encounter two primary types of these enigmatic points. Curvature singularities are where the curvature of spacetime itself becomes infinite, like the very center of a black hole. Then there is the more speculative idea of a naked singularity, one not hidden behind an event horizon. The cosmic censorship hypothesis, a still unproven conjecture, suggests that nature abhors such a spectacle and that all singularities are always modestly veiled by an event horizon, preventing their infinite weirdness from affecting the outside universe. This idea is formalized in the Hawking-Penrose theorems, which use global geometry to show that singularities are a generic feature of our cosmos, not just rare exceptions. But are these points of infinite density physically real, or are they merely artifacts telling us that Einstein's theory has reached its limits? Most physicists believe it is the latter, that a theory of quantum gravity would step in to replace the infinite curvature with something else, perhaps an ultra-dense but finite knot of spacetime, as suggested by loop quantum gravity. This profound question of what lies beyond a singularity naturally fuels our imagination. Could a singularity be a bridge rather than an end? The theoretical possibility of an Einstein-Rosen bridge, or wormhole, suggests that a singularity might be a tunnel connecting two distant regions of spacetime, or even two separate universes. While such cosmic shortcuts are likely unstable and would require exotic matter to remain open, their mathematical existence hints that the most extreme failures of our physical theories might also be the gateways to our greatest discoveries. The equations of general relativity contain a stunning possibility, a hidden doorway woven into the very fabric of the cosmos. Known as a wormhole or an Einstein-Rosen bridge, this theoretical tunnel could connect two distant points in spacetime, creating a shortcut that defies our conventional sense of distance. First proposed by Albert Einstein and Nathan Rosen in 1935, These structures are valid solutions to the field equations, yet they come with a profound catch. To remain open and stable enough for anything to pass through, a wormhole would require a form of exotic matter. This is not merely antimatter, but something far stranger, a substance possessing negative energy density that would effectively push the spacetime tunnel outward, counteracting the immense gravitational force that strives to crush it shut. Physicist Kip Thorne, who rigorously explored these concepts, noted that wormholes are theoretically possible but may be unstable or require unknown physics. This exotic matter would have to violate what is known as the average null energy condition, a standard rule for normal matter, making its existence a central point of debate. We can classify these hypothetical passages into two broad types. Non-traversable wormholes, like the original Einstein-Rosen model connected to a black hole singularity, are effectively one-way streets to a dead end. A traversable wormhole, however, is the stuff of interstellar dreams. For it to be a useful shortcut, it must be free of event horizons and contain manageable tidal forces, allowing a traveler to pass through safely. The specific geometry for such a stable passage is described by the Morris-Thorne metric, a mathematical blueprint that explicitly requires the exotic matter to keep the wormhole's throat, its tunnel, propped open. Even with this exotic ingredient, quantum effects at the microscopic scale might destabilize the tunnel, causing it to collapse into a singularity or snap shut in an instant. Science fiction has long been captivated by this idea, with Christopher Nolan's film Interstellar providing a visually stunning depiction of a wormhole as a shimmering spherical gateway to another galaxy. But beyond the wonder of rapid travel lie deep physical paradoxes. If you could enter one end of a wormhole while the other end is accelerated to near light speed, a time dilation effect would occur. The two mouths would become desynchronized so that entering one could mean exiting the other not just in a different place, but in a different time. This immediately opens the door to potential violations of causality. You could potentially travel back to a time before you entered and interact with your past self, creating unresolvable logical contradictions like the famous grandfather paradox. So, could such reality-bending tunnels exist in our universe? The immense challenges suggest that if they do, they are likely microscopic, flickering in and out of existence at the Planck scale, far too small for any human journey. Their formation might have been possible in the chaotic froth of the very early universe, but maintaining them would demand a control over physics we do not yet possess. This speculative leap into wormholes forces us to confront a fundamental question about the universe's own rules. Does nature possess a built-in mechanism that forbids such bizarre phenomena from ever being seen? This line of inquiry leads directly to a principle designed to protect the sanctity of physics from such infinite weirdness. Nature seems to shield us from its own deepest chaos. The cosmic censorship hypothesis, a profound conjecture by Roger Penrose, proposes a fundamental rule for our universe that singularities, those points of infinite density where physics breaks down, are always modestly clothed by an event horizon. Penrose himself famously stated that nature abhors a naked singularity, suggesting a built-in cosmic modesty that preserves the predictability and order we rely upon. Without this protective veil, the unpredictable, lawless physics at a naked singularity could influence the outside universe, making cause and effect impossible to determine and shattering our ability to make scientific predictions. This idea comes in two distinct forms. The weak cosmic censorship suggests that singularities formed from realistic gravitational collapse, like a dying star, will always be hidden within a black hole, forever invisible to outside observers. The strong form takes it even further, proposing that no singularities, not even those from the Big Bang itself, should ever be visible to any observer. But is this censorship absolute? Scientists test this by running sophisticated numerical simulations of collapsing stars, particularly those with rapid rotation. A collapsing, spinning star carries a tremendous amount of angular momentum, and this rotation can potentially counteract the inward pull of gravity, perhaps delaying the formation of an event horizon and exposing the singularity, if only for a moment. Some theoretical models, like the collapse of certain types of dust or exotic matter fields, have indeed produced mathematical counterexamples, naked singularities that appear perfectly valid within the equations of general relativity. Yet, the critical question remains, are these realistic or merely mathematical curiosities that would never form in the real, messy cosmos? The most likely place to challenge censorship is in the formation of a Kerr black hole, the type that forms from a rotating star. Its unique structure includes not just an event horizon but an ergosphere, a region outside where spacetime itself is dragged around by the black hole's spin. Within this swirling maverick of frame dragging, the rotational energy is so extreme that it might, under very specific conditions, allow for a glimpse behind the cosmic curtain. What would happen if we could actually observe a naked singularity? The very fabric of reality as we understand it would be called into question. The deterministic nature of physics would vanish, replaced by unpredictable chaos emanating from the singularity. As we push these ideas into the quantum realm, the question shifts. Does quantum gravity, with its discrete spacetime, enforce censorship even more strictly, or could it allow for a controlled peek at these ultimate frontiers? The relentless spin of a cosmic giant may yet hold the key to what the universe so carefully hides. A spinning planet does far more than just curve the space around it. It actively pulls that space into a swirling vortex. This phenomenon, known as frame dragging or the Lense-Thirring effect, reveals that mass alone does not dictate gravity. Motion has a profound say as well. Predicted by Joseph Lenz and Hans Thirring in 1918, it is a subtle but crucial nuance to Einstein's general relativity, showing how a rotating body like Earth twists the very fabric of spacetime around itself, like a spinning ball submerged in a thick fluid. The principal investigator of the Gravity Probe B mission, Francis Everett, perfectly described the experimental goal as seeing the Earth drag spacetime around with it. This satellite, equipped with incredibly precise gyroscopes, spent over a year measuring this minuscule twist. The effect is so tiny that the predicted angle of drift was a mere fraction of a degree per year, yet the probe's measurements confirmed it, directly observing how our planet's rotation stirs the cosmic fabric. We can understand this by thinking of a gravitomagnetic field. Just as a moving electric charge creates a magnetic field, a moving or spinning mass generates this analogous gravitational field. It is this gravitomagnetic field that exerts an additional, gentle tug on nearby objects, causing the orbital plane of a satellite to slowly precess or wobble around the rotating Earth. The implications become far more dramatic around cosmic giants. Around a rapidly spinning neutron star or a black hole, frame dragging becomes an overwhelming force. The effect creates a region outside the event horizon called the ergosphere, where spacetime is dragged around so violently that nothing, not even light, can remain stationary. It is like being caught in a cosmic whirlpool where the very space you occupy is moving faster than you can swim against it. This intense dragging is crucial for powering the relativistic jets that scream from the poles of active galactic nuclei, channeling vast amounts of energy across the universe. We even see evidence of this in pulsar timing arrays, where the precise clock-like ticks from spinning neutron stars are minutely altered by the frame-dragging effects of their binary companions. So could we ever harness this cosmic swirl? One speculative idea involves using the frame dragging around Earth itself for ultra-precise satellite navigation, correcting for this subtle relativistic drift to achieve even greater accuracy. This realization that motion warps space in a dynamic, swirling dance naturally directs our gaze to how this warped cosmos can bend the very light traveling through it. A massive galaxy cluster warps the space around it into a colossal natural lens. This phenomenon, gravitational lensing, bends the path of light from objects lying far behind it, magnifying and distorting their images in a dramatic confirmation of Einstein's general relativity. Astronomer Fritz Zwicky first grasped its potential in the 1930s, suggesting that lensing could reveal the unseen mass of the universe, a prediction that now underpins our hunt for dark matter. We observe this cosmic magnification in several distinct forms. Strong lensing creates spectacular effects, where the gravity of a foreground cluster is so powerful that it can twist the light of a background galaxy into perfect Einstein rings or slice its image into multiple mirrored arcs. The Einstein cross, for instance, is a stunning example where a single distant quasar appears as four distinct images arranged around a central galaxy. Weak lensing is far more subtle, producing a slight statistical shearing or stretching of countless background galaxies. By meticulously measuring this tiny distortion across vast fields of view, astronomers can map the invisible scaffolding of dark matter that permeates the cosmos. Then there is microlensing, where a single star or planet passing in front of a distant star causes a temporary, precise brightening, a method we use to discover worlds that would otherwise remain forever hidden. The applications are profound. By analyzing these cosmic mirages, scientists can measure the expansion rate of the universe, the Hubble constant, with remarkable precision. The bullet cluster provides perhaps the most compelling evidence, where the visible matter of two colliding clusters is separated from the bulk of their mass, which is mapped through gravitational lensing, proving that dark matter is a real, physical entity that does not interact with normal matter. This ability to use space-time itself as a telescope allows us to peer deeper into the cosmos than ever before, revealing infant galaxies from the dawn of time. What other hidden realms might come into focus through these natural cosmic lenses? As we map the universe's large-scale structure through this warped light, we are inevitably drawn to question the ultimate destiny of this vast, expanding tapestry. Our universe's final chapter may be a slow, cold fade into darkness. This ultimate fate, known as the Big Freeze or heat death, is the most likely scenario if dark energy continues to dominate. In this distant future, the relentless acceleration will push galaxies beyond our cosmic horizon, their light forever lost to us. One by one, stars will exhaust their nuclear fuel and wink out, leaving behind cold, dead remnants. Even black holes will eventually evaporate away through Hawking radiation, leaving a vast, empty void where the temperature approaches absolute zero and no further work can be done. It is a future of maximum entropy where the universe has reached a state of total equilibrium, a silent and final end. Yet another, more violent possibility exists, the Big Rip. If the repulsive force of dark energy were to intensify over time, it would not just push galaxies apart, it would tear the very fabric of reality. First, galaxy clusters would be ripped asunder. Then, individual galaxies. The force would grow until it overcame the gravity holding stars together, shredding planetary systems. In the final, terrifying moments, it would rip apart atoms, nuclei, and even space-time itself. Cosmologist Lawrence Krauss captured the decisive role of dark energy. stating that the future of the universe is written in its properties. The path we take hinges on the equation of state of dark energy, a value represented by the parameter W, which describes the relationship between its pressure and density. If W is exactly -1, the cosmological constant model holds, leading to the steady big freeze. But if W is less than -1, the phantom energy scenario takes over, dooming the cosmos to the Big Rip. Our current measurements from supernova data and the cosmic microwave background point toward the cosmological constant, favoring the cold, quiet end. This fate is also tied to the universe's curvature and critical density. We live in a universe that appears geometrically flat, meaning its density is very close to the critical value that balances expansion and collapse. In a flat universe dominated by dark energy, the expansion continues to accelerate forever, precluding a dramatic collapse. This leads us to the profound question of how our fleeting human existence fits into these cosmic timelines. All of recorded history is less than a blink in the lifespan of a star, and our civilization is a momentary spark in a journey lasting trillions of years. Does this vast, indifferent future render our lives meaningless, or does it make the brief, bright flash of consciousness we experience all the more precious? But must this be the only end? Some cosmological models offer a more cyclical vision. Could our universe be just one heartbeat in an infinite series? The idea of a cyclic universe suggests a rebound, a big bounce where a previous cosmos collapsed to a hot, dense state before expanding again into our own. Other theories propose that the vacuum of space is not in its true lowest energy state, and a catastrophic event called vacuum decay could create a bubble of true vacuum that expands at the speed of light, rewriting the laws of physics in its wake and obliterating our universe in an instant. While these are speculative, they challenge the finality of the Big Freeze and invite us to consider that our universe's story might be part of a much grander, perhaps infinite, narrative. This contemplation of ultimate endings and beginnings forces us to confront a haunting coincidence. Why does a universe destined for such a cold, empty end possess laws that so perfectly allow for our existence in its brief, warm middle years? Our existence in this cosmos is a powerful filter on what we can observe. This simple but profound idea is the Anthropic Principle, a concept that forces us to confront a startling bias in our view of the universe. We do not see a random cosmos, we see one that is compatible with our presence as observers. The physicist Brandon Carter, who first named this principle, stated that the universe must be such as to admit the existence of observers, weaving a direct thread between the vast laws of cosmology and the specific requirements of biology. This perspective offers a powerful explanation for the eerie fine-tuning of the universe's constants. It suggests that if the strength of gravity or the nuclear forces were even slightly different, we simply would not be here to notice. The principle is often split into two forms. The weak anthropic principle notes that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. We find ourselves on a planet with liquid water, orbiting a stable star at a time billions of years after the Big Bang, because only under these specific conditions could we have evolved. The strong anthropic principle takes a more controversial stance, proposing that the universe must have properties that inevitably lead to the emergence of life. This distinction is crucial, as one is a statement about our specific circumstances, while the other implies a deeper teleology, a universe somehow compelled to create observers. The anthropic principle finds its most natural home within the multiverse framework. If an infinite ensemble of universes exists, each with different physical laws, then it is no surprise we find ourselves in one of the rare habitable ones. Our universe is not special, it is just our address in a vast cosmic archipelago. Consider the specific recipe for carbon-based life. For carbon, the essential element of life, to form in abundance inside stars, a very precise resonance must exist in the carbon-12 nucleus. This resonance is a delicate balance of the strong nuclear force, and if it were off by even 1%, the universe would be devoid of the carbon needed for planets and people. The Anthropic Principle says this is not a miracle, it is a prerequisite for our conversation. Critics, however, argue that this reasoning can border on a tautology, a self-evident truth that explains nothing. They ask if it stifles scientific inquiry by accepting fine-tuning as a given rather than seeking a deeper physical theory that might predict these constants from first principles. Does the principle close a door to understanding, or does it open a new one, guiding us toward theories like the multiverse that can naturally accommodate our existence? This cosmic context profoundly shapes our search for extraterrestrial life. We are not searching for life under any conditions, but for life that exists in a universe with our same physical laws, likely based on similar chemistry, around stars not too different from our own. The Anthropic Principle defines the playing field, telling us where to look and what to look for. It forces a humbling reflection. Are we the universe's intended outcome, or just a fortunate accident in one of its more hospitable neighborhoods? This contemplation of our own cosmic context inevitably draws our attention to the fundamental limits of what we can ever hope to see. Our cosmic horizon is a cage built not from walls but from time itself. This boundary of our observable universe, stretching 46 billion light-years in every direction, is the ultimate limit of our vision, a frontier defined by the finite speed of light and the age of the cosmos. Cosmologist Janna Levin perfectly described this limit as a historical artifact, a consequence of how long light has had to travel to reach us rather than any true physical edge. Everything we can possibly see, from the nearest star to the most distant quasar, exists within this immense but finite sphere. This leads to a profound distinction between two types of horizons. A particle horizon marks the distance to the farthest objects whose light has finally reached us after the Big Bang. It is our past, the limit of what we can observe. An event horizon, in contrast, is a limit on our future. It defines the most distant points from which light emitted today could ever hope to reach us in an accelerating universe. As expansion speeds up, this event horizon is actually shrinking, slowly cutting off more and more of the cosmos from our future view. The volume enclosed by our particle horizon is often called the Hubble volume, a region where the expansion velocity is less than the speed of light. Beyond this volume, galaxies are receding so quickly that their light can never cross the gulf. This is why the cosmic microwave background is so pivotal. It is the afterglow from our own particle horizon, the oldest signal we can ever detect. This horizon was set by the early period of inflation, which stretched a tiny, causally connected patch into a region far larger than what we can now observe. This means that the entire universe we see was once a minuscule, homogeneous neighborhood, which explains its stunning uniformity. Yet, this very fact hints at a staggering reality. The universe beyond our horizon is likely unimaginably vast, possibly infinite, filled with regions forever separated from us by an unbridgeable expanse. Will we ever see those regions in a universe dominated by dark energy? The answer is a definitive no. More and more galaxies will be pushed beyond our horizon, their light fading from view as if they never existed. This shrinking island of visibility forces us to ask what secrets are lost to us forever, and how much of the true cosmic story remains hidden just beyond the edge of sight. This limitation of our view is intimately tied to the energy of the void itself. the mysterious force that dictates our ultimate isolation. The void of space is not truly empty. It seethes with a restless energy, a quantum fizz of virtual particles that constantly wink in and out of existence. This is the vacuum energy, a fundamental concept from quantum field theory that represents the lowest possible energy state of a field. When we try to calculate its density, the result is a number so catastrophically large it defies comprehension, suggesting a vacuum energy density around 120 orders of magnitude greater than what we actually observe. This staggering mismatch is the cosmological constant problem, and it represents one of the most profound failures in modern physics. The great physicist Steven Weinberg did not mince words, calling it the worst theoretical prediction in the history of physics. The cosmological constant, that term Einstein introduced and then discarded, is precisely this vacuum energy manifested in the equations of general relativity. The problem is that our two most successful theories, quantum mechanics and gravity, give us two completely different answers for the energy of nothingness. To understand why, we must look at zero-point energy. Even at absolute zero, quantum fields are never completely still. They exhibit tiny, irreducible fluctuations. The energy of these fluctuations, when summed over all possible vibrational modes, gives a theoretically infinite result. Physicists use a mathematical trick called renormalization to subtract away these infinities and get finite, usable answers for particle interactions. But for gravity, which is sensitive to the absolute value of energy, this subtraction feels arbitrary, like we are simply discarding an inconveniently large number to match observation. This is the heart of the fine-tuning problem. The vacuum energy seems to be balanced on a razor's edge, cancelling out to a value incredibly close to zero, but not quite, allowing for the accelerated expansion we see. One proposed solution involves a principle called supersymmetry. This elegant theory posits that every known particle has a superpartner. The beauty is that the contributions of these partner particles to the vacuum energy could perfectly cancel out the enormous quantum contributions from ordinary particles, driving the net energy towards zero. The catch is that if supersymmetry exists, it must be a broken symmetry at the energy scales we can access, because we have not detected any of these superpartners. Another, more philosophical resolution comes from the Anthropic Principle within the multiverse. If countless universes exist with every possible value of the vacuum energy, then we naturally find ourselves in one where this value is small enough to allow galaxies to form and life to evolve. A significantly larger vacuum energy would have caused the universe to expand so rapidly that no stars or planets could ever coalesce. So the eerily small value we measure might not be a law of physics, but a local bylaw of our cosmic neighborhood. This immense discrepancy forces us to question the very nature of gravity itself. Could our understanding of Einstein's theory be incomplete on the largest scales, pointing toward a deeper, more fundamental description of the cosmos? Einstein's equations might not be the final word on gravity. For decades, the dominant solution to cosmic mysteries like galaxy rotation has been to invoke dark matter, an unseen substance providing extra gravitational pull. But a small, persistent group of physicists asks a different question. What if we are simply using the wrong formula? Modified Newtonian dynamics, or MUND, is the most prominent of these alternative theories. Its founder, Mordechai Milgrom, suggested that maybe we do not need dark matter if we tweak gravity appropriately. MUND proposes that on the scale of galaxies where accelerations become incredibly faint, Newton's laws and by extension Einstein's require a small modification. Instead of the force of gravity falling off with the square of the distance, it changes to a different behavior in these ultra-low acceleration environments. This single tweak can remarkably reproduce the flat rotation curves of spiral galaxies without any dark matter halo, matching the observed speeds of stars with surprising accuracy. The theory has evolved into more sophisticated relativistic versions, like tensor vector scalar gravity, or TVS, which attempts to incorporate Mann's successes into a full framework compatible with the tenets of relativity. Another class of alternatives are F of R gravity theories, which modify how spacetime curvature responds to matter and energy in Einstein's field equations. These theories often introduce new fields or change the way gravity propagates, effectively creating an extra-gravitational effect that mimics dark matter or even dark energy on cosmic scales. Yet each alternative faces significant hurdles. While Mann excels at explaining the dynamics of individual galaxies, it struggles on larger scales. It has a difficult time accounting for the precise gravitational lensing observed in massive galaxy clusters, which strongly points to the presence of a large amount of unseen mass. The bullet cluster, where the majority of the mass revealed by lensing is clearly separated from the visible matter, remains a profound challenge for any theory that tries to explain away dark matter through modified gravity alone. Furthermore, the landmark detection of gravitational waves from colliding neutron stars delivered a critical test. The gravitational waves and the accompanying flash of light arrived at virtually the same time, traveling over 100 million light-years. This demonstrated that gravity, in the form of spacetime ripples, travels at the speed of light to within 1 part in a quadrillion. Many alternative theories predicted a different speed for these waves, and this observation ruled out a wide swath of them, reinforcing general relativity's core prediction. The debate is far from settled, however. Intriguingly, Mann often makes more accurate predictions for the motions of stars in certain dwarf galaxies than standard dark matter models do. This persistent success in specific regimes keeps the idea alive, forcing cosmologists to refine their models and consider more complex dark matter scenarios. So where does this leave us? The core question remains, is general relativity a complete theory of gravity, or is it an incredibly precise approximation that breaks down under the most extreme or subtle conditions? New experiments are poised to probe this frontier. The Laser Interferometer Space Antenna, or LISA, will detect low-frequency gravitational waves from merging supermassive black holes, offering a new regime to test these theories. Meanwhile, ultra-precise maps of the cosmic microwave background and the large-scale structure of the universe will continue to constrain any proposed modifications. This fundamental quest to understand gravity is not just an abstract exercise. It has a direct and practical impact on the technology we use every single day. High above the Earth, a constellation of satellites silently corrects for the warping of reality itself. Your phone's GPS is a continuous, real-world test of cosmic relativity, relying on a network of atomic clocks orbiting at 20,000 kilometers per hour. Each of these clocks experiences two competing relativistic effects that must be precisely calculated, or the entire system would fail within minutes. According to physicist Clifford Will, GPS is a daily validation of Einstein's theories, a testament to its profound real-world relevance. The first correction is for special relativity. Because the satellites are moving at high speed relative to an observer on the ground, their onboard clocks tick slower due to kinematic time dilation. If we did not account for this, the satellite's timing would fall behind by about 7 microseconds each day. The second and larger effect comes from general relativity. The satellites orbit in a region where Earth's gravitational field is weaker than it is at the planet's surface. In this less curved spacetime, clocks actually tick faster. This gravitational time dilation causes the satellite clocks to gain about 45 microseconds per day. The net result is a gain of 38 microseconds daily, a seemingly tiny amount that has dramatic consequences. Since the positioning system relies on the speed of light to calculate location, and light travels nearly 300,000 kilometers in a single second, a timing error of just 1 microsecond translates to a positional error of 300 meters. Without these constant relativistic adjustments, the GPS in your car or phone would accumulate errors of more than 10 kilometers per day, rendering turn-by-turn navigation useless. This is only possible because of the incredible precision of atomic clocks, which use the vibration of cesium or rubidium atoms to measure time with near-perfect accuracy. This practical application forces us to look beyond our planet. Could future interstellar navigation systems rely on the predictable pulses from distant neutron stars, using these cosmic lighthouses and their own extreme relativistic effects to guide spacecraft through the galaxy? The same principles that guide your drive to the store are essential for understanding the most extreme objects in the cosmos. A city-sized object spins hundreds of times every second, its surface a solid crust of iron nuclei locked in a crystalline lattice. This is a neutron star, the collapsed core of a giant star that went supernova. Within this sphere, barely 20 kilometers across, you find a mass greater than our entire sun crushed to the density of an atomic nucleus. A single sugar cube of this material would weigh billions of tons on Earth, a mass comparable to every human being combined. It is an environment where gravity is so intense that it overcomes the very forces that keep atoms apart, squeezing protons and electrons together to form a sea of neutrons. Jocelyn Bell Burnell, who co-discovered the first pulsar in 1967, perfectly described these objects as fantastic cosmic clocks, highlighting their incredible regularity. The discovery was initially so precise and repeating that her team half-jokingly labeled the signal LGM for little green men, before realizing they had found something entirely new in nature. The clock-like ticks are the beams of radiation from a pulsar, a rapidly spinning neutron star with an off-axis magnetic field. As the star rotates, these lighthouse-like beams sweep across the sky, and if Earth lies in the path, we detect a pulse of radio waves with a regularity that rivals the best atomic clocks. This precision makes them perfect tools for testing general relativity. In a binary system, the orbit of two neutron stars provides an exquisite laboratory. The most famous of these, the Hulse-Taylor binary pulsar discovered in 1974, consists of two neutron stars dancing around each other. By meticulously timing the pulses from one of them, astronomers Russell Hulse and Joseph Taylor observed that the orbit was slowly decaying. The two stars were spiraling inward, losing energy at the exact rate predicted if they were emitting gravitational waves. This was the first indirect but spectacular confirmation of Einstein's ripples in spacetime, a discovery that earned them the Nobel Prize. The internal structure of a neutron star is a mystery layered like an onion. Beneath the thin, solid crust, we encounter a neutron superfluid, a bizarre state of matter that flows with zero friction. At the very core, the true nature of matter is unknown. The immense pressure might crush neutrons into a soup of their constituent quarks, creating a strange quark star, or it might form exotic states of hyperons or other particles. This is described by the equation of state, a theoretical model that relates pressure to density and determines the star's maximum possible mass. If a neutron star accretes more matter, perhaps from a companion star, and exceeds this limit, it will undergo a catastrophic collapse, vanishing behind an event horizon to become a black hole. The intense gravity of a neutron star also creates dramatic frame dragging, twisting the local spacetime around it as it spins. This warping can be measured through subtle effects on the timing of its pulses, providing another stringent test for general relativity. These cosmic laboratories, born from stellar death, push our understanding of matter to its absolute limit. What secrets about the fundamental forces are locked within their ultra-dense cores? The quest to understand such extreme objects inevitably leads us to consider even more exotic and theoretical relics from the universe's birth. A cosmic string would be a scar on the universe, a flaw in reality left over from its earliest, most violent moments. These hypothetical filaments are thought to be thinner than a proton yet denser than a mountain range, stretching across billions of light years like cracks in frozen cosmic ice. The physicist Alexander Vilenkin used that very analogy to describe their formation during the rapid cooling of the Primordial Universe, when the fabric of spacetime underwent a phase transition, much like water freezing into ice. Just as ice can form with cracks and fissures, spacetime may have crystallized with these one-dimensional topological defects. Their existence is a key prediction of many grand unified theories that attempt to merge the fundamental forces. The primary property defining a cosmic string is its tension, an immense density that is not dependent on the string having any thickness. This incredible tension gives a cosmic string its gravitational power. It would not pull objects toward it with a standard gravitational pull, but would instead create a unique kind of lensing effect. Light from a galaxy behind a string would be split into two identical images, a perfect cosmic mirage with no distortion. Even more dramatically, if a string were to oscillate or snap, it would send powerful ripples through spacetime, generating a background of low-frequency gravitational waves that observatories like LISA might one day detect. We search for their signatures in the oldest light we have, the cosmic microwave background. A moving cosmic string would create a telltale step-like discontinuity in the temperature of this radiation, a sharp edge between a slightly warmer and a slightly cooler patch. Sophisticated computer simulations of cosmic evolution model how these strings would interact with the formation of galaxies, potentially weaving the large-scale structure of the cosmos. The hunt is on to find these ghostly scars. Future telescopes with unprecedented sensitivity, like the Square Kilometre Array, will scan the skies for the unique gravitational lensing and temperature jumps that could betray a string's presence. What would their discovery mean for our understanding of cosmic inflation? It would be a direct window into the energy scales of the universe's first fraction of a second, confirming that the early cosmos underwent the kind of dramatic phase transitions that inflation suggests. Finding a cosmic string would be like discovering a fossil from the moment reality itself was taking shape. This leads to a truly mind-bending proposition that our dimensional reality and everything in it might be a holographic projection from a distant two-dimensional surface. The universe might be a hologram, a cosmic projection from a distant two-dimensional surface. This is not science fiction, but a serious proposal grounded in the physics of black holes and string theory. The holographic principle suggests that all the information describing our three-dimensional reality, every galaxy, planet, and person, could be entirely encoded on a remote boundary, like a three-dimensional image emerging from a flat screen. The physicist Juan Maldacena, who formulated a precise version of this idea, stated that the holographic principle is a deep connection between gravity and quantum field theory. His work, known as the AD/CFT Correspondence, provides a mathematical blueprint. It demonstrates that a gravitational theory operating in a hypothetical anti-de Sitter space is completely equivalent to a quantum field theory without gravity living on its lower dimensional boundary. They are two different descriptions of the same fundamental reality, a cosmic duality where gravity and spacetime are not primary but emergent phenomena. This framework has been extended to our own universe, which resembles a different geometry called de Sitter space. If the holographic principle holds true here, then we, and everything we see, might be a projection from the edge of the observable cosmos. A key player in this informational picture is entanglement entropy. The quantum entanglement between different regions on the boundary is what weaves together the very geometry of spacetime in the bulk. Reduce that entanglement, and space itself begins to pull apart. This profound link creates a dramatic puzzle known as the black hole firewall paradox. If an astronaut falls toward a black hole's event horizon, what do they experience? Quantum mechanics suggests they should feel nothing special, crossing the horizon smoothly. But the holographic principle, focusing on the preservation of information, implies that the horizon should be a searing wall of fire, a violent discontinuity that protects the cosmic code from contradiction. This paradox forces physicists to choose between the smoothness of spacetime and the purity of quantum information, a stark conflict at the frontier of our understanding. String theory models provide a playground for exploring these ideas, suggesting that the particles and forces we perceive are like the vibrating pixels of a grand cosmic display. So if reality is fundamentally informational, what does that say about the nature of existence itself? Are the laws of physics simply the operating system of a universe built from bits? This realization that information is the true currency of the cosmos compels us to examine the quantum glue that holds it all together. Two particles separated by a galaxy can share a single quantum identity. This is quantum entanglement, a phenomenon Einstein famously called spooky action at a distance, where the measurement of one particle instantly determines the state of its partner, no matter the space between them. For decades, this seemed like a bizarre quantum quirk with no connection to the large-scale cosmos. But a revolutionary idea, known as the ER=EPR conjecture, now suggests that these spooky links might be the very threads weaving the fabric of spacetime together. Proposed by Juan Maldacena and Leonard Susskind, this idea connects two seemingly unrelated concepts. EPR stands for Einstein, Podolsky, and Rosen, who first highlighted the strangeness of entanglement. ER stands for Einstein and Rosen, who discovered the mathematical possibility of wormholes. The conjecture proposes that every pair of entangled particles is, in fact, connected by a microscopic wormhole, an Einstein-Rosen bridge. Susskind captured the profound implication, stating that entanglement builds the geometry of spacetime. This means the ghostly connection of quantum mechanics is not separate from gravity. It is what creates the smooth, continuous geometry of general relativity. The holographic principle provides the stage for this connection. In the holographic universe, the entangled quantum bits on the lower dimensional boundary create the geometric connectivity of the higher dimensional spacetime we experience. The more entanglement there is between different regions on the boundary, the smoother and more connected the spacetime in the bulk becomes. If you were to reduce that entanglement, space itself would begin to fracture and pull apart. This framework offers a new way to think about black hole interiors. If two black holes are entangled, the conjecture suggests their interiors are physically connected by a wormhole, even if their exteriors are separated by vast cosmic distances. This provides a potential solution to the black hole information paradox, as information falling into one black hole could, in principle, travel through this wormhole bridge to escape the other, preserving quantum information. We see a laboratory-scale version of this in quantum teleportation experiments. While we are not teleporting matter, scientists can teleport the quantum state of a particle across a room or even between satellites. In these experiments, entanglement is the resource that allows the information to be transferred instantly, acting as a kind of channel. According to ER=EPR, this channel could be visualized as a fleeting, microscopic wormhole. This hints at a universe far more deeply interconnected than we ever imagined. Could the cosmic web of galaxies be mirrored by a vast, underlying web of quantum entanglement? Does the unity we perceive in the cosmos stem from these fundamental, invisible threads? The idea of using entanglement for faster-than-light communication remains a dream, as no usable information can be sent this way without a conventional signal. But the deeper message is staggering. The spookiness of the quantum world may not be a bug in reality, but the feature that builds reality itself. This bridge between the smallest and largest scales of existence forces us to look back to the universe's first moments, when this quantum fabric was first woven into the cosmos we know. The first moments of the cosmos were a furnace of pure potential. In the immediate aftermath of the Big Bang, the universe was not filled with stars or galaxies, but with a seething, opaque plasma of fundamental particles, a primordial soup where energy densities were so extreme that relativity and quantum mechanics were inextricably fused. This entire primordial era acts as a unique laboratory, a place where the fundamental forces of nature were likely unified into a single superforce. Cosmologist James Peebles perfectly captured its significance, stating that the early universe is a laboratory for fundamental physics, a place where conditions exist that we could never hope to recreate on Earth. We can trace this cosmic history back to the Planck epoch, the very first sliver of time, 10 to the negative 43 seconds after the beginning. Here, the energy was so immense that gravity itself would have been as strong as the other forces, and the very concepts of space and time as we know them break down, becoming a frothing quantum foam. This was the era of grand unification, where the strong nuclear force, the weak nuclear force, and the electromagnetic force were all one. As the universe expanded and cooled, these forces underwent a series of cosmic phase transitions, freezing out into the distinct interactions we recognize today. A critical mystery from this period is baryogenesis, the process that created the profound imbalance between matter and antimatter. In the earliest moments, particles and antiparticles should have been created in equal amounts, destined to annihilate each other into pure radiation. Yet we live in a universe made almost entirely of matter. Some slight asymmetry, some violation of symmetry in the laws of physics, must have favored the production of matter over antimatter by about 1 part in a billion, leaving behind just enough substance to build every galaxy and star. The evidence for this entire hot Big Bang model is etched into the cosmos itself through Big Bang nucleosynthesis. During the first 3 to 20 minutes, the universe had cooled just enough for protons and neutrons to begin fusing, but it was still too hot and dense for them to build anything heavier. In this brief window, the relativistic expansion rate, dictated by the density of matter and radiation through Einstein's equations, was perfectly tuned to produce a specific mix of light elements. The models predict that about 75% of the ordinary matter should be hydrogen, 25% helium, and trace amounts of deuterium, helium-3, and lithium. When we look at the oldest, most pristine regions of the universe, this is precisely what we find, a stunning confirmation that our understanding of these first few minutes is correct. These initial conditions were the blueprint for everything to come. The slight variations in density from quantum fluctuations, stretched to cosmic scales by inflation, were the gravitational seeds that would later pull in dark matter and gas, eventually forming the vast cosmic web of galaxies. This entire narrative, from a unified superforce to the first atomic nuclei, forces a profound question about the nature of existence. What is the true nature of the void from which all this complexity spontaneously emerged? The void of space is a restless sea. What we perceive as pure emptiness is, according to quantum field theory, a dynamic arena of constant activity. At the tiniest scales, pairs of virtual particles and their antiparticles spontaneously blink into existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other and vanishing back into the void. These are quantum fluctuations, a fundamental feature of reality where nothing is never truly nothing. This ceaseless fizz is more than a microscopic curiosity. It may be the very engine that set our entire cosmos in motion. The physicist Lawrence Krauss captured this radical idea, stating that the universe can come from nothing if nothing is unstable. He challenges our traditional notions of creation, suggesting that the quantum vacuum, with its inherent instability, provides a complete physical picture for the origin of everything. This dynamic vacuum is central to both relativity and quantum mechanics. In Einstein's theory, empty space possesses a fundamental energy density, a pressure that can drive the cosmos apart. In the quantum world, this energy manifests as these temporary particle pairs, a testament to the vacuum's vibrant, unpredictable nature. The link to our cosmic history is profound. The theory of cosmic inflation suggests that a tiny patch of this seething quantum foam was stretched to an astronomical size during the universe's first explosive moment. The minute density variations in that primordial foam, those random fluctuations, were magnified to cosmic proportions. They became the gravitational seeds, the blueprints for all the structure we see today, from the great cosmic web of galaxies to the tiny temperature variations we detect in the cosmic microwave background. Those patterns in the oldest light are the direct, fossilized imprint of quantum jitters from the dawn of time. We can even witness the reality of these vacuum fluctuations in laboratory experiments. The Casimir effect demonstrates this beautifully. When two uncharged parallel metal plates are placed extremely close together in a vacuum, they are gently pushed toward each other. Why? Because the narrow gap between the plates restricts the kinds of virtual particles that can pop into existence, while outside the plates, a fuller spectrum of fluctuations can occur. The greater pressure from the outside pushes the plates together, a measurable force generated by the energy of seeming nothingness. Similarly, at the edge of a black hole, these quantum fluctuations are responsible for Hawking radiation. When a particle-antiparticle pair appears just outside the event horizon, one may fall in while the other escapes, causing the black hole to slowly lose mass and evaporate. The black hole radiates by consuming the negative energy of the infalling particle, a process fueled entirely by the restless vacuum. So what does this mean for the nature of existence? If the universe emerged from a quantum fluctuation in a metastable void, can we truly say that something came from nothing? Or is our definition of nothing simply inadequate, referring not to a state of non-being, but to a physical vacuum brimming with potential? This forces a deep philosophical shift, blurring the line between empty space and the source of all creation. If our entire cosmos is but one fluctuation in a vast, eternal void, what other universes might be bubbling into existence beyond our perception? This profound connection between the quantum vacuum and cosmic structure naturally draws our attention to another, nearly ghostly messenger from the universe's violent birth. Billions of ghostly particles are streaming through your body every second. These are cosmic neutrinos born in the heart of the Big Bang and in the furious furnaces of stars, and they barely notice the world of matter. They are cosmic phantoms capable of passing through light years of lead without a single interaction, yet their subtle behavior holds profound secrets. Nobel laureate Arthur B. MacDonald revealed a key piece of this puzzle, stating that neutrinos have mass which challenges the standard model. This tiny, non-zero mass forces physicists to rewrite their theories and opens a new window into the universe's most violent events. Neutrinos travel at velocities so close to light speed that they are living embodiments of relativistic effects, their internal clocks slowed by time dilation from our perspective. Their study is a perfect marriage of cosmic relativity and particle physics, where the rules of Einstein meet the quantum realm. We detect these phantoms in monumental experiments buried deep underground, like the Super Kamiok and detector in Japan, a colossal tank of ultra-pure water surrounded by sensitive light sensors. When a rare neutrino does interact, it creates a faint flash of light, a cosmic whisper captured in the darkness. One of their most bewildering traits is neutrino oscillation. As they travel through space, neutrinos spontaneously change their identity, morphing between three different types or flavors: electron, muon, and tau. This very phenomenon is what proves they have mass, as a massless particle would be frozen in a single state forever. This discovery alone upended decades of established physics. A dramatic example arrived in 1987, when a star went supernova in the Large Magellanic Cloud. Detectors on Earth registered a burst of neutrinos a few hours before the visible light reached us. These messengers had escaped the collapsing stellar core ahead of the shockwave, providing a direct snapshot of a star's death throes and confirming that these particles travel at near light speed. Beyond these stellar explosions, we search for the faintest relic of all, the cosmic neutrino background. This is a sea of low-energy neutrinos left over from the first second after the Big Bang, a fossil even more ancient than the cosmic microwave background. Detecting this primordial whisper would give us a direct look into the universe's infancy, long before atoms even formed. So what ultimate secrets could these ghostly carriers carry? Their elusive nature and quantum behavior might hold the key to the final unification, a theory of quantum gravity. They travel unscathed through regions of space that would shred other particles, possibly carrying unedited information from the edge of a black hole or from the first instant of time. What could they tell us about the dark matter that binds the galaxies, or the fundamental symmetries that shaped all of creation? A silent constellation of 3 spacecraft will soon form a perfect triangle 1,000,000 miles on each side, listening for the deepest hum of the cosmos. This is the Laser Interferometer Space Antenna, or LISA, a next-generation observatory designed to detect gravitational waves at frequencies far lower than any ground-based detector can perceive. Its target is the slow, stately dance of supermassive black holes, binary systems with masses millions of times greater than our Sun, whose mergers will create a low rumble in spacetime that has been echoing through the universe for billions of years. By measuring these waves with exquisite precision, LISA will test whether Einstein's predictions hold true in these most extreme gravitational environments, or if subtle deviations appear that point toward new physics. This is the new era of experimental relativity, where our theories are not just confirmed, but rigorously stress-tested at the very limits of imagination. The Nobel laureate Barry Barish captured this frontier spirit perfectly, stating that gravitational wave astronomy is just beginning, its full potential still waiting to be unlocked. Beyond LISA, the James Webb Space Telescope peers back to the cosmic dawn, studying the formation of the very first galaxies. How did these structures assemble so quickly after the Big Bang within the framework of cosmic relativity? Their early light, stretched and bent by the expanding universe, provides another stringent test, probing gravity on the largest possible scales. On Earth, a different kind of hunt is underway using pulsar timing arrays. These projects use the universe's most natural clocks, spinning neutron stars, to detect the faint, background hum of gravitational waves from countless merging supermassive black holes across the cosmos. By monitoring the precise arrival times of these pulses across a network of pulsars, astronomers can sense the minute stretching and squeezing of spacetime as these long wavelength waves pass by. Another groundbreaking approach is atomic interferometry, where the wave-like nature of atoms is used to measure gravitational forces with incredible sensitivity. In these experiments, clouds of ultra-cold atoms are dropped in a vacuum, and their quantum wave functions are split and then recombined. The slightest difference in the gravitational field along the two paths creates a detectable shift in the interference pattern. This technology could lead to experiments that test the equivalence principle, the foundational idea that all objects fall at the same rate in a gravitational field, with a precision 100 times greater than ever before. Imagine a satellite in orbit dropping two spheres made of different materials, perhaps platinum and titanium, into free fall around Earth. If one falls even slightly faster than the other, it would shatter a core tenet of general relativity and open the door to a revolutionary new understanding of gravity. What surprises might these experiments reveal? Perhaps we will find that gravitational waves travel at a speed imperceptibly different from light, or that black holes have a subtle structure or hair that general relativity does not permit. Maybe the data will reveal an interaction between dark matter and gravity that we have never before detected. Each of these possibilities carries the seed of a scientific revolution, a clue that our current theory, for all its beauty, is an approximation of a deeper, more complete truth. Could the cumulative weight of this new evidence finally lead us to a new theory of gravity, one that seamlessly unites the cosmic and the quantum? This relentless experimental drive, this need to test our most cherished ideas against the cold, hard data of reality, forces a profound shift in perspective. It moves us from the equations on the page to the very meaning of the reality they describe. Your personal timeline is a single thread woven through a vast, four-dimensional tapestry. This is the profound implication of the block universe theory, a view of reality where past, present, and future do not succeed each other but simply are, all equally real and permanently existing. Einstein's own reflection that the distinction between past, present, and future is a stubborn illusion points to this eternalist perspective, a direct consequence of his theories. In this framework, the flow of time we feel is not a fundamental feature of the cosmos, but a feature of our consciousness, a psychological arrow projected onto a static reality. This idea, known as eternalism, suggests that you as a child and you as you are now, and every future version of you, all exist simultaneously in the grand structure of spacetime. Your life is not a movie being played, but a completed DVD, with the laser of your awareness simply moving from one chapter to the next. This directly confronts our deepest intuition about free will. If the future is already out there, just as fixed and real as the past, then are our choices truly free, or are we just following a script written in the geometry of the cosmos? The twin paradox is not just a puzzle about clocks, it is a philosophical window into this reality. The traveling twin does not just age slower, they literally take a shorter path through the block universe, their world lines stretching less between the event of departure and the event of return. The relativity of simultaneity shatters the idea of a universal now. Two events that are simultaneous for one observer can happen at different times for another, depending on their motion. There is no privileged present moment that everyone in the universe agrees upon. This elevates the role of the observer to a new level. It is not just that we see the universe, but that our state of motion fundamentally shapes which slice of the block we call our present. What does this mean for the nature of knowledge and truth? Scientific facts must be framed relative to an observer's reference frame, challenging the classical ideal of absolute, God's eye view objectivity. Our ethics, built on the assumption that the past is fixed and the future is open to our decisions, must also adapt. If a future tragedy is just as real as a past one, does our moral responsibility change? Yet, this cosmic perspective can also be a source of profound meaning. It suggests a universe of immense structure and connection, where every moment of joy, every act of courage, and every discovery is eternally etched into the fabric of reality. Our journey through these 35 insights, from the warping of spacetime to the whispers of the quantum vacuum, ultimately leads us back to ourselves. Does cosmic relativity make the universe more comprehensible or more mysterious? It gives us a powerful, mathematical framework to predict and understand the cosmos, yet it reveals a reality so alien to our daily experience that it continually humbles us. It shows us that the universe is far stranger, more interconnected, and more wondrous than we ever imagined, inviting us to forever explore the deepest mysteries of existence. The early 20th century crackled with a sense of impending revolution in physics. Classical mechanics, the majestic edifice built by Isaac Newton, had reigned for 2 centuries, describing a universe of absolute space and absolute time. But by the late 1800s, cracks had begun to show. James Clerk Maxwell's elegant equations for electromagnetism had unified light, electricity, and magnetism, yet they created a troubling paradox, suggesting that the speed of light should be constant for all observers, a notion that clashed directly with Newton's laws of motion. This theoretical tension was brought into sharp focus by a meticulous experiment conducted by Albert Michelson and Edward Morley in 1887. They sought to measure the Earth's motion through the hypothetical luminiferous ether, the presumed medium for light waves. Their result was a stunning null, a profound silence that shook the foundations of physics. The ether did not seem to exist, and the speed of light remained stubbornly unchanged, a puzzle that would haunt the next generation of thinkers. At the same time, a small anomaly in the heavens defied explanation. The planet Mercury, the Sun's closest companion, exhibited a slight wobble in its orbit, a slow precession of its perihelion that Newtonian gravity could not fully account for. For decades, this tiny discrepancy was a nagging whisper that something was missing from our understanding of gravity. Into this intellectual ferment stepped a young patent clerk in Bern, Switzerland. Albert Einstein was deeply engaged with these empirical puzzles, possessing what historian Abraham Pais described as a profound connection to the data of the world. In 1905, his Annus Mirabilis, Einstein published his special theory of relativity, which boldly discarded the ether and embraced the constancy of light speed as a fundamental postulate. This was not an overnight revelation, but the culmination of years of thought experiments, of chasing beams of light in his imagination. Special relativity resolved the electromagnetic paradoxes, but it left gravity untouched. For the next decade, Einstein wrestled with the far greater challenge of incorporating gravity into this new relativistic framework. This journey was a monumental struggle, a grueling ascent into the abstract heights of mathematics. He realized that his theory required a new language, the non-Euclidean geometry developed by Bernhard Riemann decades earlier. It was a language that described curved spaces, and Einstein, with crucial help from his friend Marcel Grossmann, had to learn it and then apply it to the cosmos. The final push in 1915 was a feverish race against the brilliant mathematician David Hilbert. a competition that ultimately culminated independently in the same profound equations. The general theory of relativity was born, elegantly explaining Mercury's orbital precession not as an anomaly, but as a natural consequence of the Sun's warping of spacetime. But a theory, no matter how beautiful, must face the test of observation. The opportunity came with the total solar eclipse of May 29, 1919. Sir Arthur Eddington led a famous expedition to the island of Principe to measure the positions of stars near the Sun's obscured limb. If Einstein was right, the Sun's gravity would bend the starlight, making the stars appear slightly out of place. The results, when announced, made Einstein a global celebrity overnight. The measured deflection matched the prediction of general relativity, not Newton's theory. It was a paradigm shift, a change in the very fabric of scientific understanding, driven by a blend of individual genius, collaborative effort, and the relentless pressure of empirical evidence. This historical struggle echoes in every modern quest, from the search for dark matter to the hunt for gravitational waves. It reminds us that our cosmic view is never final, but always evolving, shaped by the curious minds willing to listen to the whispers of the universe and brave enough to rewrite its rules. What future anomaly, currently ignored as a minor glitch, will be the catalyst for the next great revolution in physics? Our journey through cosmic relativity reveals a universe far grander and more mysterious than our ancestors ever dreamed. We have seen how space-time bends, how time stretches, and how the vacuum itself holds the key to creation. These ideas do more than solve puzzles about black holes and expanding galaxies. They touch the very core of our existence, challenging what we know about reality, time, and our own humble place in this vast cosmic arena. The great astronomer Carl Sagan once reminded us that somewhere, something incredible is waiting to be known. That sense of wonder is the true legacy of this exploration. So I ask you, how has this voyage shifted your perspective? Does the fluidity of time change how you value each moment? Does the scale of the cosmos make you feel insignificant or profoundly connected to something magnificent? Share your reflections in the comments below. I am genuinely curious to hear your thoughts. If unraveling these mysteries with us has sparked your curiosity, please subscribe for more journeys to the edge of understanding. Our cosmic adventure is far from over, and the next great discovery is just a click away.